So let V be a vector space let V be a vector space of dimension n. Dimension n with ordered basis beta is equal to V1, V2, so on, Vn. Then any V belonging to V has a representation then any V has a representation of the form this V is equal to A1 V1 plus A2 V2 plus so on plus AN Vn. Then V beta, then we have this notation V beta. Then this is defined as a column vector of these coefficients. So this is A1, A2 up to AN is called the coordinate of V relative to the basis beta. So once we are given any vector in a vector space, then we can always find out this coordinate vector related to the given ordered basis beta. And in fact, conversely, if we are given any coordinate vector, if we are given a coordinate vector v beta, and we are given an ordered basis beta, then we can also reconstruct the vector v. In fact, given v beta, if we are given this coordinate vector, given v beta and the basis beta is equal to v1 through vn, we can reconstruct v by the formula. In fact, it comes from the definition of this coordinate vector. V is equal to a1 v1 plus a2 v2 plus so on plus an vn. So actually, if we are given a vector space and v is in a vector space, beta is the basis, then we can have this representation and then we can construct this coordinate vector related to the basis beta. But once we are given this coordinate vector related to some ordered basis beta, and we are also given the beta, we are given the vectors which are inside this beta, then we can express this linear combination a1 v1 a2 v2 an vn. Then this linear combination will give us this vector v again. So therefore, once we are given a vector, we can construct the coordinate vector, and once we are given the coordinate vector and a basis, we can reconstruct the v using this linear combination. So this we have already done. Now let's come to define the matrix representation of a linear transformation. So let's do it here. Matrix representation of a linear transformation. So how do we define this matrix representation of a linear transformation? First, whenever we define a linear transformation, we must have two vector spaces. So therefore, we will choose two vector spaces of dimension m and n respectively, and then choose their ordered basis And then to express every element of V, we then know that every vector in V has a coordinate representation related to its given ordered basis. Then the images of the vectors in V which are inside W. Then every vector in W would also have a coordinate vector representation related to its ordered basis. Then from all that thing, we will define the matrix. We will express a given linear transformation in the form of a matrix. So now let us do it. So let V and W be the vector spaces over the same field F. Over the same field F with dimension of V is equal to M, dimension of W is equal to N, and let beta be the ordered basis of, so let's call the dimension as, because at the end we will then get the matrix of the form N cross M, M cross N. Let beta is equal to V1, V2, so on, Vn be the ordered basis of V, and gamma is equal to W1, W2, so on, Wm be the ordered basis of W. Also let T from V into W be a linear transformation. Suppose we have this T from V into W is a linear transformation. Now, as we have seen earlier, that if we choose any vector from V, then it has a coordinate vector, it is a coordinate representation related to the basis beta. And if we are given any vector in W, then it is a coordinate representation related to the basis gamma. So if V belongs to V, then V beta, then V has a coordinate related to the basis related to beta. That is we have this V related to the basis beta. Let's define it to be a vector of this form. So it's x1. Let this be the coordinate vector of V related to the basis beta. Now again, since T of V, now V was chosen from V, so therefore T of V will be in W. Then it has a coordinate representation. Again, since T of V is in W, thus it has a coordinate representation related to the basis gamma. Related to the basis gamma of W. That is, we have this thing. So we can write T of V related to the basis gamma. So let's call this is equal to y1, y2, so on, ym, because we have taken this W as a vector space of dimension m, so it will have m vectors in its basis. So therefore, we can express always this v has this coordinate representation, and also this t of v, which is a vector in W, has this kind of a coordinate representation. Then from the definition of v, now since, let's write it again, since v beta is equal to x1, x2, xn. Now let's write it in the form of a transpose. We have this v is equal to x1 v1 plus x2 v2 plus so on xn vn. Okay. But now this v is a vector in V, and if we apply the linear transformation t on this vector, we can get, then applying t, we get t of v. This will be equal to, now using the fact that t is a linear transformation, so therefore we can write this t of v is equal to x1 t of v1 plus x2 t of v2 plus so on plus xn t of vn. Okay. So since this t is a linear transformation, so we can write these scalars outside t and express this t of v in this way: x1 t of v1, x2 t of v2 plus so on xn t of vn. So this equation comes from the coordinate representation of v related to the basis beta, and we can express then t of v in this shape. Now again, also we have, but also from the coordinate representation of t of v, also from the coordinate representation of t of v, we have जो हमने अभी डिफाइन किया था t of v beta, gamma, it was equal to y1 y2 ym, and we know the basis of w that was chosen as w2 wm. So gamma is this basis, and we have the coordinate of t of v related to the basis gamma as this thing. So therefore we can write. So therefore we have t of v. It is equal to w1 y1 y2 w2 plus so on plus yn w. Let's call this equation as equation number 2. Okay. But now again, looking at this equation, t of v is equal to this thing. Here we have these vectors t of v1, t of v2, t of vn. Now, since these are the images of the vectors, they are inside W. So therefore, each of these t of vi's also has a coordinate representation related to the basis gamma. So, but again, we can write since t of vi since t of vi belongs to W. Thus, each t of vi has a coordinate representation thus each t of vi has a coordinate representation related to the basis gamma. related to gamma. So we have T of E1. This can be written as A11 W1 plus A21 W2 plus so on A M1 WM. This we can do because T of V1 is an element of W. It's a vector in W, so therefore T of V1 can be written as a linear combination of the basis gamma of W with scalars from the field F. And similarly, T of V2, now this is again in W, so we can again express it as a linear combination of the vectors Wi's from the basis gamma with scalars from the scalar field F. So here we can write this is equal to A12 W1 A22 W2 plus so on A M2 WM. And similarly so on. And similarly the last vector T of Vn, which is the image of the basis vector Vn, this can also be expressed as A1n W1 A2n W2 plus so on A Mn Wm. So actually we are here trying to define the relation between V beta, the coordinate vector of V related to the basis beta, and the coordinate vector of T of V related to the basis gamma. Since V and T of V are related, we will try to see how these coordinate vectors are related to each other, how V beta is related with T of V gamma. And for this thing, we know that T of V is equal to this thing. Now, since T of Vi is inside W, so therefore each T of Vi has a coordinate representation related to the basis gamma. So we have T of V1 has this linear combination. We are assuming T of V2 has this linear combination over the vectors from the basis gamma. And similarly, T of Vn has this representation related to the basis gamma. Why are these coefficients? Why? The coefficients A11 up to Amn are scalars from F, which is the underlying field over which both V and F are the vector spaces. Now coming back to our situation that we have this T of V. Coming back to our equation number first, we have T of V is equal to x1 T of V1, x2 T of V2 plus xn T of Vn. But now, here we had expressed what is this T of V1. T of V1 is equal to this equation. तो हम इसको यहाँ पे substitute करेंगे in equation number first. Then we are also given T of V2. We have expressed it in this form. So वहाँ पे हम यही value इसका substitute करेंगे. So therefore from equation first we have. So now from equation first we have, so what we have T of V is equal to x1, but now T of V1 has a coordinate representation related to the basis gamma, so therefore we can have for T of V1, so it is A11 W1 W1 W2
A1 to W
A M1 WM, then plus x2 A1 to W1 then A2 to W2 plus so on A M2 WM, then so on, plus the last equation was xn, and for xn we had the coefficient, we have T of V1 with it, so it has this representation, so it is A1n W1 A2n W2 plus A Mn WM. But again, what is the value of T of V? Now T of V has a coordinate of the coordinate of T of V related to the basis gamma. It's equal to y1, y2, yn. So that's why we have this equation number 2. T of V is equal to y1 w1, y2 w2 plus ym wm. Now we can use the equation number 2 here in place of T. So thus, or we have now T of V, this is equal to y1 w1 plus y2 w2 plus so on plus ym wm. But now this is equal to this equation. Now here we will rearrange the terms. We will first write the coefficients of w1, then the coefficients of w2, and then the coefficients of wm. So here the coefficients of w1 are, it is a11 x1, then here it is a12 x2, and so on. And here we have a1n xn. So it's a1n xn, and all these are the coefficients of w1. Then plus, then second the coefficients of w2. So it is a21 x1, a22 x2 plus so on plus a2n xn, and these are all the coefficients of w. Then plus so on. And the last is the coefficients of wm. So it's a m1 x1, a m2 x2 plus so on a mn xn wm. So therefore we have this representation. Now here we have left hand side is w1 y1 w2 y2 wm ym, and the right hand side is this thing. But now here we can look at this equation. We can compare the coefficients of y1, because the coefficient of y1, because here we have w1, here we have w1, we can compare its coefficients. So therefore y1 has this representation, therefore y2 will get this representation, and ym will have the coefficient of wm as its representation. So now comparing the coefficients. Comparing the coefficients of wi's. So we have y1. This is the coefficient of w1. So here the coefficient of w1 is this linear combination, this equation. So it is a11 x1, then a12 x2, then so on a1n xn. And then y2, this is equal to a21 x1, a22 x2, then so on a2n xn, and so on. Similarly, ym, this is equal to am1 x1, am2 x2 plus so on, then amn xn. But now this can be put in the matrix form, which can be written in the matrix form. In the matrix form as, तो left hand side में जो हम matrix लिखेंगे, that will be the matrix of y's. So this y1, y2, ym. Now the right hand side is, first we write the matrix of coefficients. So it is a11, a12, a1n, a21, a22, a2n, then am1, am2, amn. And now here we can multiply it with the x's. So it's x1, x2, xn. ठीक है, तो इस तरह से हमें मिल गई मैट्रिक्स फॉर्म ऑफ दिस रिप्रेजेंटेशन. So now if we define, now if we define this T, this is just a notation. So let's write T beta gamma. If we define this as this matrix, जो हमने last page पे define की, it was A11, A12, so on A1n, then A21, A22, A2n, AM1, AM2, AMN. तो जो हमने यहाँ पे मैट्रिक्स लिखी, now we will denote this matrix by T beta gamma. So then we have now see what we have. Now this y1, y2, ym, this was the coordinate vector of T of v relative to the basis gamma. And this x1, x2, xn, this we had defined, it was the coordinate vector of the vector v related to the basis beta. So therefore from this equation, this is tv gamma. Now this is this is denoted by t beta gamma, and this was our v beta. So therefore from this equation, so therefore we have this y, which is t of v related to the basis gamma. Now this is equal to t beta gamma, and then here we have the coordinate vector of, this is with respect to beta. So ये equation हमें मिली. Now in this equation, so this is the relation, this equation defines the relation between the coordinate vector of v related to the basis beta and the coordinate vector of t of v related to the basis gamma. And the relation is this coordinate vector of t of v related to the basis gamma is equal to t of beta gamma and the coordinate vector of v related to the basis beta. Now here the matrix here the matrix T with beta gamma is known as the matrix of linear transformation T is known as a matrix of linear transformation T from basis beta to basis gamma. This writing this basis beta to basis gamma is just to highlight that we have this linear transformation T from a vector space V whose ordered basis is beta and to the vector space W whose ordered basis is gamma. In fact, if we have a linear transformation T from vector space V into W, then this matrix of T will depend on the basis beta and gamma. If we change the basis, we will get a different matrix. And similarly, if we change the basis gamma, we will get a different matrix. So this all these coefficients, A1, A2, AN, and all these coefficients in this matrix, they actually depend on the linear transformation T, and they also depend on the basis beta and gamma. So here we can add where we have defined these coefficients, where the scalars are the scalars from F, which depend on these depend on T, beta, and gamma. Okay. So this is how we define the matrix representation of a linear transformation T. So once we are given a linear transformation, then once we are given two vector space, let us quickly revise it now. We are given a linear transformation from V into W. V has the ordered basis beta, W has the ordered basis gamma. Then every vector V has this coordinate vector representation related to the basis beta, and then T of V also has a coordinate representation related to the basis gamma. But now when we have V is equal to this linear combination, then T of V will have this linear combination. But now T of VI's, they have the coordinate representations with respect to related to the basis gamma. Then we are using them here. We are expressing every T of VI as a linear combination of the vectors from W, from the basis gamma of W. Now, using these equations in this T of V, we get this equation, but now T of V has its coordinate vector representation related to the basis gamma as this in this form. Then here comparing the coefficients of Wi's, we get the value of y1, y2, yn in terms of these things. Then this gives us a matrix system. And in this matrix system, this left-hand side is the coordinate vector of T of V related to the basis gamma. This is defined to be the matrix of linear transformation now. And this was originally the coordinate vector of V related to the basis beta. Now, when we are given some question, now how we will, what we have the procedure for writing its coefficient matrix, we don't have to do so much process. हमें वहाँ पे इतना सारा नहीं लिखना है. So let's recall the procedure. The procedure for finding the matrix of T. T from V into W. So first step is we are given the basis beta. It is V1, V2, Vn. And then we are also given the basis gamma, which is W1, W2, Wm. Then what we did to construct this matrix, we evaluated these images. We evaluated T of V1, और हमने इसको लिखा था, this was equal to A11, W1 plus A21, W2 plus so on, AM1, Wm. So we can look back here. तो यही हमने लिखा था, this was a T of V1, it was equal to this equation. ये system मैं यहाँ पे अब लिख रहा हूँ. Now similarly, T of V2, since it is a vector in W, so it has the linear combination in the basis gamma. So it is written as A12, W1, then A22, W2 plus so on, plus AM2, Wm. And similarly, T of Vn, this was equal to A1n, W1, A2n, W2, plus so on, AMN, Wm. So therefore, what we are doing in this thing, we are actually choosing this ordered basis beta and evaluating the images of these vectors, T of V1, T of V2, and T of Vn, and then writing these images as the linear combinations in the basis gamma, because this T of Vi is inside W and it is basis gamma, so we can have this linear representation. And similarly, actually, we are just trying to evaluate the coordinate vectors of T of Vi's, where Vi's are the vectors from the basis beta. Then the matrix of T's. Then immediately from here, we can define this matrix of T, beta, gamma. Now this is like this. तो यहाँ पे जो हमारे पास पहला coordinate vector था T of V1, it has this coordinate representation. Since the coordinate representation of a vector is a column vector, तो जो यहाँ पे पहले coefficients है, we will write them as the first column of this matrix T beta gamma. तो यहाँ पे हम लिखेंगे elements A11, A21, AM1. Then T of V2, it is like this. It is A12, A22, AM2. Now the last column is A1n, A2n, AMN. So actually this is the matrix. The first one is the coordinate representation of T of V1. तो इसको हम इस तरह से भी लिख सकते हैं. this is first column, second column, and third column, and so on. So इसको हम इस तरह से लिख सकते हैं. This is T of V1 with respect to gamma. Then the second column is T of V2 with respect to gamma, and so on. And the last column is T of Vn with respect to gamma. ठीक है, तो इस तरह से बनाते हैं matrix representation of a linear transformation. Now we have just less than a minute left, so I think we should stop here now. तो आपने ये नोट किया?
हाँ सर.